In the last two cases, we consider the characteristic equations has a distinct eigenvalues or repeated eigenvalues. Both cases, actually the eigenvalues are real numbers. Now we'd like to consider the case of the complex number. So characteristic equations has a complex eigenvalues of the lambda sub 1 and lambda sub 2. Always the lambda sub 1 and the lambda sub 2 appears as a complex conjugate. Lambda sub 1 is expressed alpha plus I betas, and alpha and beta are real numbers. And the lambda sub 2 is expressed alpha minus I betas. Then k sub 1 is an eigenvector corresponding to the eigenvalue of the lambda sub 1s. So also the k sub 1 has a real part of the b sub 1s and the imaginary part of the I b sub 2s. So b sub 1 and b sub 2s, both real vectors with real components. Eigenvectors corresponding to the lambda sub 2 is given by the conjugate of the k sub 1. So k sub 2 equal b sub 1 minus I b sub 2. Because consider the homogeneous equations, if you take a complex conjugate of this both sides of the equations, actually the t is a real numbers, so this is equal to the dt complex conjugate of the x equal a is a matrix, so is a real component, so a x. If the x is a solution of the differential equations, also the complex conjugate of x becomes the solutions. So general solutions is expressed x equals c sub 1 k sub 1 exponential lambda sub 1 t plus c sub 2 k sub 2 exponential lambda sub 2 t plus blah 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 up to the c sub n k sub n exponential lambda sub n t's. But each term actually is expressed as a function with a complex numbers. So we'd like to transform this equation into a more convenient form of the equations. We consider the following two terms in general solutions of the y sub 1 and the y sub 2. So this corresponds to the y sub 1 and this corresponds to the y sub 2. But y sub 1 and y sub 2 are functions with complex numbers. So we'd like to transform this y sub 1, y sub 2 into a more convenient form of equations. So we consider the following two terms of the y sub 1, y sub 2 and they expressed. So k sub 1 is equal to the b sub 1 plus I b sub 2. We substitute. Lambda sub 1 is alpha plus I betas. Then equation is expressed this way using the Euler's formulas. Then we can expand these equations. So first terms correspond to the real terms, and the second term is multiplied by I, so imaginary terms. And also the y sub 2 is expressed the same way. K sub 2 is a b sub 1 minus I b sub 2. And the lambda sub 2 is alpha minus I betas. So it becomes next lines. And if we expand, then we combine to form the real terms and the imaginary terms. Then we'd like to express the general solutions with the real functions. So we create x sub 1 and x sub 2 using this equation. This is the definition of the x sub 1s. By sum up the y sub 1 and y sub 2s, it becomes just the real functions. B sub 1 cosine beta t minus B sub 2 sine beta t times exponential alpha t's. And x sub 2 is defined with this equation, 1 over 2i times y sub 1 minus y sub 2. This is the definition of the x sub 2s. The equation is expressed b sub 1 sine beta t plus b sub 2 cosine beta t times exponential of alpha t's. So y sub 1 and y sub 2 are complex functions, but it transforms into the real functions of x sub 1 and x sub 2s. Using these real functions, we can express the general solutions of the homogeneous differential equations using these ways. Then all the terms is expressed with the real functions. Then I'd like to show you the example. So solve the following homogeneous system of the equation, this equation. So this corresponds to the A. Then first of all, we'd like to solve the characteristic equations. Characteristic equation is a determinant A minus lambda I equal 1 minus lambda minus 2 1 minus 1 minus lambda equals 0. This equation is expressed lambda square plus 1 equals 0. So lambda equal plus minus I. So for the lambda sub 1 equal I, we'd like to find out the corresponding eigenvectors. By substituting I into this, we could build the equation for k sub 1s. So it becomes 1 minus I minus 2, 1 minus 1 minus I, and k sub 1 equals 0. To satisfy this equation, we can find that k sub 1 is expressed 2 times 1 minus I. Also, for the lambda sub 2 equal minus I, this is actually correspond to the lambda sub 2. It's a complex conjugate of the lambda sub 1s. Then you can substitute into the equations. It's a 1 plus I minus 2, 1 minus 1 plus I, k sub 2 equals 0. So we could find the k sub 2 is that 2, 1 plus I. From this equation, we could confirm k sub 2 actually the complex conjugate of the k sub 1. So from these equations, we can find out alpha equals 0, beta equal 1, and b sub 1 is a 2, 1, b sub 2 equals 0, minus 1. So we discovered this alpha, beta, b sub 1, and b sub 2. So using these expressions, we could write down the general solutions. This way, c sub 1 times x sub 1. This is x sub 1. C sub 2 times x sub 2s. Okay, this is a general solutions when the characteristic equations has a complex eigenvalues. Okay, this is the end of this session.